Okay, Taylor polynomials and approximations. We're getting ready to begin probably one of the most important parts of BC. And each year on your AP Calculus BC exam, the sixth FRQ is typically a Taylor or Maclaurin series polynomial problem. So, you know, in the beginning when we started sequences in series and we were doing all these tests, we asked why. Why are we doing this? And I talked to you about how a long time ago, back in the day, people didn't understand how to differentiate and how to integrate transcendental functions like the sine of x. And so what they decided to do was they would build these polynomials that mimicked the sine function, and they kept on adding terms and terms and terms, and as they kept on adding more terms, this became closer and closer to sine, and as you take all these terms out towards infinity, it actually becomes the sine function. And they were able to integrate these and differentiate these polynomials much, much easier, just using your basic power rules. So what we're going to start doing is you know, figuring out why is it that the sine of x is modeled by x minus x to the third over 3 plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial, and on down the line. Where does that come from? Because it's not random. Okay, there's a reason that it is this pattern, and so we're going to start building these. Now, in order to get one of those, we have to start somewhere, and so we're going to start with the most basic graph here. We want just one point to be the same, not all the points of a graph to be the same, but one, okay? So to find a polynomial function p that approximates another function f, begin by choosing some number c in the domain of f, at which point f and p have the same values. So the y values are the same, okay? They share that point. Now p is not a very good approximation of f right there, okay? But just around c, at exactly c, they share the same value. Now this is going to be an important notation. The approximating polynomial is said to be expanded about c, or centered at c. Okay? And the requirement that p of c equals f of c also means that p passes through c comma f of c. But as I was saying, you know, my red line here, p is not a very good approximation of f of x. And, you know, there's a million, even more than a million, there's typically actually an infinite number of polynomials that pass through that point right there, an infinite number of lines. So how do we make it even better? Okay, the way we're going to do that is to make sure the slope of p be the same as the slope of f at the point c comma f of c. And so in order for that to be true, you know, thinking of slope, your derivatives at c are going to have to be equal to each other. Okay, so those are two very, very, very important things. All right, so first degree polynomial approximation of f of x equals e to the x. For the function f of x equals e to the x, find a first degree polynomial function p sub 1 of x, which is equal to a sub 1 of x plus a sub 0, whose value and slope agree with the value and slope of f at x equals 0. All right, so basically what we want is we want a line. And I know that because it says p sub 1 of x is a sub 1 of x plus a sub 0. Really, I mean, I see mx plus b there, and it's a first degree polynomial. That's going to be a line. We want to find a line that mimics f of x equals e to the x around x equals 0. I just rewrite this down because I need to fill in numbers for a sub 1 and a sub 0. And remember, what we need to know is the slope of f of x at e to the x, or f of x equals e to the x at x equals 0. Okay, I need to know the slope. I want the slopes to be the same. So, for f of x equals e to the x, the slope at 0 is 1. We took the derivative of e to the x, we substituted 0, and we got 1. So I'm going to rewrite my equation here as p sub 1 of x is 1x plus a sub 0. Now, we're going to use the other piece of information, okay? Recall that p of x and f of x share a point at x equals 0, so their y values must be the same as well. And f of 0 is 1, so I'm going to substitute 0 comma 1 into my line, and I'm getting my y-intercept there to be 1. So p sub 1, or of x, is 1x plus 1. And you can see the graph there. Okay, the curved line is e to the x, and the straight line is the polynomial we just found, 1x plus 1. You'll notice that at x equals 0, they are very, very close. I'm going to zoom in here a little bit. Right around 0, centered at 0, okay, the line is mimicking the graph of y equals e to the x. But the further you get away from 0, the more error you have there. Okay, as you can see, points close to x equals 0. The two are reasonably close to each other. However, as you move farther away, the approximation becomes less accurate. So to improve the accuracy, we can impose another condition, and that is the second derivatives must also agree when x is equal to 0. This is the second degree polynomial. Piece of 2 is 1 plus x plus 1/2 x squared. Then you have f of x equals e to the x. And you notice that they're very accurate, just a little bit longer than the line was. Okay? All right. So here we have constructing a table comparing the values of the polynomial. We're still doing e to the x. And we have piece of 3. This is the third degree polynomial. And I want you to take out your calculator and fill in these values. You can push pause here, but then just notice for values surrounding 0, they should be relatively close. And then when you get out to -1 and +1, you should see more error. Clearly, as you can see, at 0, they're the same. And then as you get further and further from 0 on either side, you're getting more and more error. All right. So Taylor and Maclaurin polynomials. The polynomial approximation for f of x equals e to the x given in the first example is expanded about c equals 0. For expansions about an arbitrary value of c, it's really convenient to write the polynomial in this form. And the only difference is we have x minus c here. In the other ones we just had, like if c was 0, you just have a sub 0 plus a sub 1 times x plus a sub 2 times x squared plus a sub 3 times x to the third plus dot dot dot. But if c is some other number other than 0, like for example, suppose you were expanding it about c equals 1, then you'd have to do a sub 0 plus a sub 1 times x minus 1 plus a sub 2 times x minus 1 squared plus a sub 3 times x minus 1 to the third. Excuse me. Now, the reason I have this up here, we're really interested in who are these coefficients, okay? We need to figure that out. And so the way we're going to be doing that is we're going to be looking at derivatives. And so I took the first derivative, piece of m, and we're going to know that the derivative of a sub 0, that's just a number. That's going to be 0. Then the derivative of a sub 1 times x minus c is just a sub 1. And then I'm taking the derivative of each consecutive term. And so I'm pulling the exponent out and subtracting 1 from the exponent. Second derivative, again, the derivative of a sub 1 is 0, so I'm not writing that. And then the derivative of 2a sub 2 times x minus c is just 2a sub 2. And then I'll be pulling out the exponents and subtracting 1 from the exponent, each one down the line. Now I'm not going to rewrite, for example, where it says 2 times 3a sub 3 times x minus c. I'm not, going to write that as 6a sub 3 because I want us to notice a pattern here. Each derivative you take, you'll notice that you're going to have n times n minus 1 times n minus 2. You should be thinking about that as n factorial there. Okay? So the nth derivative, when you're pulling that out, n times n minus 1 times n minus 2 times dot 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 times 2 times 1, that is n factorial. So what we're going to do now is we're going to let x equal c because we're still trying to figure out what these coefficients, a sub 0, a sub 1, all of those are. Okay? And I know this is a lot and it's really confusing, but I just want to show when you let c or x equals c, p sub n of c is a equals 0 or a sub 0. Okay? That's going into that top equation there and letting x equals c. Everything is going to multiply to 0 except for the a sub 0, and you're left with a sub 0 there. The first derivative, when you substitute c, we're going to get a sub 1. Second derivative, when you substitute c, we're going to get 2a sub 2. Third derivative, 2 times 3 times a sub 3. And the nth derivative, n factorial times a sub n. So here, f of c is equal to a sub 0. f prime of c is equal to a sub 1, f double prime of c over 2 factorial is equal to a sub 2, f triple, the third derivative evaluated c divided by 3 factorial is equal to a sub 3, and the nth derivative evaluated c over n factorial is equal to a sub n. Remember, where I'm getting these f's from is that the y values are the same. So p sub n is evaluated at c is equal to f of c. The first derivative evaluated at c is equal to f prime of c. The second derivative of p evaluated at c is going to be equal to the second derivative of f evaluated at c. And then for that second derivative there, looking at p sub n double prime of c equals 2 a sub 2, all I did was I divided by 2. So the p became the f because those two are equal. The second derivative evaluated at c are equal. And then I divided by 2. And 2 is 2 factorial. And then for p sub n, the third derivative of p sub n evaluated at c equals 2 times 3 times a sub 3. Remember that the third derivatives are equal. So I replaced p sub n, the third derivative, with the f, the third derivative of f, and I divided by the 2 times 3, which is 3 factorial. So what you need to see here is that how does one say, these are what we're looking for here. And what we're going to do is we're going to replace a sub 0 with f of c. Okay, in the polynomial that I wrote at the top of the page, a sub 0 gets replaced with f of c. A sub 1 gets replaced with f prime of c. A sub 2 gets replaced with f double prime of c divided by 2 factorial. A sub 3 gets replaced with the third derivative of f evaluated c over 3 factorial. Now I know this is probably really confusing, and I'll go over this a little bit more in class. It'll be better if I could, see what questions you guys have. But for right now, here's what we need to know, and this really needs to be memorized here. Okay, if f has n derivatives at c, then the polynomial p sub n of x is equal to f of c. Remember, that was a sub 0 plus f prime of c times x minus c plus f double prime of c over 2 factorial times x minus c squared. And then the next one in that sequence would be f triple prime of c over 3 factorial times x minus c to the third. And then the fourth derivative of f evaluated at c over 4 factorial times x minus c to the fourth. Okay, this is what we call the nth Taylor polynomial for f at c. Now, if c equals 0, if it's centered around 0, we call it the nth Maclaurin polynomial. Okay, so a Maclaurin polynomial is a Taylor polynomial, but it's just centered at c. Taylor, you can be centered anywhere. Maclaurin has to be centered at c equals 0. So again, this needs to be memorized. One thing that will help you is you should notice that the derivative is equal to the degree of the x minus c, which is equal to the factorial you're dividing by. All right, now let's actually do one of these. I wrote that up there. Okay, I like to write these up here. We're going to create a Maclaurin polynomial for f of x is equal to e to the x. And so we're going to have to fill in everything here. I need to know who is f of c, who's the derivative evaluated at c, who's the second derivative evaluated at c, on down the line. Okay? Now here's me filling in. I knew to fill in 0 for c because this is a Maclaurin polynomial. Okay, and remember, Maclaurin polynomials are centered at 0. So I just went ahead and replaced all my c's with zeros. Now what I'm going to do is I'm going to start listing. What do I need here? In this case, I need an f of x, I need an f prime, I need an f double prime, and I need an f triple prime. So I'm going to start going down the list here. F double prime, f triple prime. And remember, I need f of 0. I need f prime of 0. So I will also be substituting 0 in each of these. We know that f of 0 is e to the 0 is 1. F prime of 0 is e to the 0 is 1. These are really boring because they're all the same. And now what I'm going to do is everywhere, I'm going to replace everything I have up there with what I just found. So f of 0, I'm going to replace with 1. F prime of 0, I'm replacing with 1. Notice that when I had my x minus 0, I just wrote that as x. F double prime of 0 was 1. 2 factorial is 2. X minus 0 is x, and then you square that. F triple prime evaluated at 0 is 1 over 3 factorial is 6. and x minus 0 is x raised to the third. And then for the nth derivative, notice every single derivative is 1, so I replace the nth derivative evaluated at 0 with 1 over n factorial, and then we have x to the n power. So that's a Maclaurin polynomial for f of x equals e to the x. That's how they built sine. It's just that we did it for e to the x. And this is just simplifying there. All right, so Taylor polynomials for f of x equals the natural log of x. And so we want to find Taylor polynomials for p sub 0, p sub 1, p sub 2, p sub 3, p sub 4 for f of x equals the natural log of x. And this time we're going to center it at c equals 1. So this isn't Maclaurin, this is Taylor as it says. So what we need to do here, again, we're going to just be filling things in. I always write this polynomial down, p sub n, or p sub n sub n, or excuse me, I can't speak right now. P sub n of x is f of c plus f prime of c times x minus c plus f double prime of c all over 2 factorial times x minus c squared plus dot dot dot. Let us begin finding p sub 0, p sub 1, p sub 2, p sub 3, and p sub 4. So in this case, we're not going to have an infinite number of terms. The first thing I'm going to do is just have one term, then it's going to be a first degree polynomial, p sub 2 is a second degree polynomial, p sub 3 is a third degree polynomial, and p sub 4 is a fourth degree polynomial. That tells me a couple things. We're really finding 5 different things here. P sub 0 is the 0 degree, so it's just a constant. P sub 1, I have to take it out to be x to the first power. P sub 2, I'm going to be taking it out, so x is to the second power, and that's where you stop with that one. With P sub 3, you're going to be taking it out to the third degree, and you're going to stop there. P sub 4, you take it out to the fourth degree, stop there. Okay, so we're starting with f of x equals the natural log of x, and we need to start taking derivatives here. We need to take out to 4 derivatives. And I know that because we're going to be going to it x to the 4th power. So these are my 4 derivatives. F prime of x is 1 over x. F double prime is negative 1 over x squared. F triple prime 2 over x to the 3rd. And the 4th derivative is negative 6 over x to the 4th. Now remember, we're centering this at 1, so I'm not going to evaluate these at 0. Because I need f of c, I need f prime of, or f of 1, I need f prime of 1, I need f prime of, double prime of 1. So substitute your 1 into each of these and get some numbers. Okay. So I've got my numbers there. So the 0 degree polynomial is just the constant. It's just f evaluated at c. It's just f evaluated at 1. So p sub 0 is 0. P sub 1 will be f of c plus f prime of c times x minus c. That's going to be f of 1 plus f prime of 1 times x minus 1. Now just fill in the numbers. 0 plus 1 times x minus 1. And we're just getting x minus 1. So the first degree Taylor polynomial for the natural log of x is x minus 1. The second degree Taylor polynomial would be f of 1 plus f prime of 1 times x minus 1 plus f double prime of 1 over 2 factorial times x minus 1 squared. Fill in what we know. If f of 1 is 0, f prime of 1 is 1, f double prime of 1 is negative 1. And then just simplify. So that there's a second degree polynomial. I know it's a second degree because x minus 1 squared will give you an x squared. The third degree polynomial. I already know that's going to be f of 1 plus f prime of 1 times x minus 1 plus f double prime of 1 over 2 factorial times x minus 1 squared plus f triple prime of 1 over 3 factorial times x minus 1 to the third. Fill in what you know. Simplify. And then finally, the fourth degree Taylor polynomial, we know it'll be f of 1 plus f prime of 1 times x minus c plus f double prime of 1 over 2 factorial times x minus 1 squared plus f triple prime of 1 over 3 factorial times x minus 3, or x minus 1 to the third, times, and on down the line until you get to the 4th degree. Fill in what you know and simplify. So this is how we build a 0 degree, a first degree, a second degree, a third degree, a fourth degree Taylor polynomial. And if I asked you for the fifth degree, you'd have to go one further. Now let's look at the natural log of x and all of these here. This, what I believe, is the first degree. This is the natural log of x. That's the curve centered at x equals 1 is the line right there. And you'll notice that around x equals 1, the line, x minus 1, is mimicking the natural log of x. And then the second degree Taylor polynomial is a little bit better. It's actually the curve that's below right now, but it's hugging that natural log function a little bit more. Then the third degree, right there, it's the one that's above in this case. It's hugging the natural log for a little bit longer. And then finally, the fourth degree is the one that's below, and it's hugging the natural log even longer. So the more pieces we add to it, the better our approximations are. And so that's going to be that for this, and then we got one more video to watch.